What if I told you a simple geometry puzzle, one from way back in 1889, has not one, not two, but three completely different and perfectly logical answers? Well, it does. For nearly 100 years, this puzzle stumped mathematicians and challenged the very idea of probability. This is the story of Bertrand's paradox.
Okay, let's just dive right in. Picture a circle. Now, inside that circle, imagine we've drawn a perfect equilateral triangle, so its corners just touch the edge. Now for the fun part. If you toss a straw so it lands across the circle, making a line, that's a chord, what's the probability that line is longer than one side of our triangle? I mean, it seems like a straightforward question. It should have one single correct answer, right? Well, that's where things start to get weird. So how on earth can a question this simple cause so much trouble? It all comes down to one single, surprisingly slippery word: random.
See, the whole problem hinges on how you decide to create a random chord. What does that even mean? Do you pick two random points on the circle's edge and connect them? Do you pick a random spot inside the circle to be the chord's midpoint? As you're about to see, how you answer that question changes absolutely everything.
This little ambiguity opens the door to three totally different, yet completely logical answers. So let's meet the three main suspects in our little mathematical mystery.
And what's so wild is that each of these feels totally legit, right? Method A is like picking a random point on a radius. Method B is like throwing two darts at the circle's rim. Method C is like dropping a pin anywhere on the circle's surface. They all sound like perfectly fair ways to get a random chord. And yet, look at the answers they give you: 1/2, 1/3, and 1/4. This is a paradox. Probability theory is supposed to be solid to give us one right answer. How can all three of these be correct?
So you can imagine, this wasn't just some fun little brain teaser. It was a serious problem. And for almost 100 years, the general consensus was that the question itself was just broken. In fact, Bertrand himself, the guy who came up with it, basically threw up his hands in defeat. His own conclusion, in French, translates to, "None of the three is false, none is exact, the question is ill-posed." He thought the whole thing was unsolvable because the term "at random" was just too vague to pin down.
For decades, this paradox was the poster child for why a core idea in probability, called the principle of indifference, was maybe a little bit flawed. The principle is simple. If you have no reason to think one outcome is more likely than another, just assume they're all equally possible. But Bertrand's paradox showed that what you call an outcome can lead you down three different paths. It was chaos.
But the story doesn't end there. Fast forward to 1973. A physicist named E.T. Jaynes comes along, looks at this century-old cold case, and says, "Hold on, the problem isn't ill-posed. You guys just aren't reading the instructions." He argued the clues were right there, hidden in what the problem doesn't say.
Here was Jaynes's brilliant move. He said, forget about trying to figure out what makes individual straws random. Instead, think about the problem statement itself. What constraints does its wording put on the answer? If you change something the problem doesn't mention, the answer shouldn't change either.
This gives us our first big clue. The problem never says how big the circle is, right? It could be the size of a coin or the size of a planet. The question is exactly the same. So, whatever method we use, it has to give the same answer for a circle of any size. We call this scale invariance.
And the second clue is just as clever. The problem doesn't give us any coordinates for the circle. It could be on your desk or in the middle of a field. It doesn't matter. So the correct solution can't change if we just slide the whole circle to the left or right. That's translational invariance.
So now, armed with these two incredibly powerful rules, scale and translational invariance, Jaynes could finally play detective. He could test our three suspects and see whose story actually held up under questioning.
So, how did they do? First, the scale test. Does size matter? Well, for method B, picking 2 points on the edge, it turns out, yeah, it does. The math for that 1/3 answer gets all weird if you change the circle's size. So, boom, suspect B is out. Next, the location test. Does position matter? For method C, picking a midpoint from the whole area. Yep, it does. That definition of random isn't consistent if you just nudge the circle. So, sorry, method C, you're out too. And just like that, after the interrogation, only one suspect was left standing. One method and one answer that respected the silent rules of the game. This whole time, the problem was never broken at all.
The correct probability, the only one that's actually consistent with all the information the problem gives us and all the information it doesn't, is 1/2. It was method A all along.
And here's the kicker. This wasn't just some abstract proof. Jaynes, being a good physicist, actually did the experiment. I mean, literally, tossing broom straws onto a circle he drew on the floor. And guess what? After 128 throws, his results lined up almost perfectly with the 1/2 probability. Case closed.
Okay, so really cool math puzzle, right? But why should we really care about this today? Well, because this way of thinking goes way, way beyond just circles and straws. It has huge implications for how science actually works.
You know, this whole idea of finding powerful rules hidden in what a problem doesn't say is basically a secret weapon for physicists. It lets them make these incredibly precise predictions about the real world, sometimes just from pure thought alone, without needing all the data.
And this isn't even new. A full 100 years before Jaynes, the legendary physicist James Clerk Maxwell used the exact same kind of logic to figure out the properties of gases. His work was revolutionary, but Bertrand's paradox came along and cast this long shadow over that kind of reasoning. Jaynes's solution basically proved that Maxwell's instincts had been right all along.
This quote from Jaynes just nails it. He's saying the trick isn't to guess which outcome is random. The trick is to figure out which problems are actually identical. And that is a much, much stronger foundation to build on.
In the end, the lesson from Bertrand's paradox is just beautiful. The answer wasn't hidden in the details we were given. It was hiding in plain sight, in the empty space, in all the things the problem didn't say. The problem's silence wasn't a flaw, it was the key.
And that just leaves you wondering, doesn't it? If this way of thinking, of listening to a problem's silence, could solve a puzzle that stumped geniuses for a century, what other massive problems, in science or anywhere else, are just waiting to be solved by paying closer attention to what the question never even thought to ask?